Okay. Chapter 6 is all about chemical bonding. The PowerPoint notes don't do a very good job at all with Section 1. And so Section 1 is actually going to be some of my own notes that I took. All right, so the majority of atoms in existence in nature are part of a chemical bond. There are actually very few elements that exist as an individual atom. Most of the time, an element or a compound is extracted from Earth's crust or from the atmosphere, and then it's separated into its individual elements. So when we talk about bonding, just in general, it's an electrical attraction between two atoms. And really the part that's attracted is the valence electrons from one atom are attracted to the nucleus of another atom. So certain atoms out there have such a strong positive nucleus that it's actually able to attract electrons from other atoms, as well as hold on to its own electrons. So one thing that we talk about when we look at bonds is potential energy. Nature favors arrangements that have a minimum potential energy. Think back to 9th grade physical science when you talked about potential energy and kinetic energy. Potential energy is at rest. So they always give the example of a boulder on the edge of a cliff. It has potential energy. When two atoms, as they get closer together, our potential energy starts to decrease. And if you look at this graph, they get closer and closer together as the potential energy decreases to the point that they bond. And then as we move these atoms further away from one another, the potential energy starts to decrease. So think of this as our boulder, and this would be the ground. So our potential decreases as the boulder gets closer to the ground. Our potential energy decreases as the two atoms get closer to one another. So this is one reason why so many more things in nature occur as compounds rather than elements. It takes less energy to bond atoms together than to break the bonds between them. And so the amount of energy it takes to separate these two is called our bond energy. So kind of keep this last sentence straight, that definition. It's the amount of energy to break a chemical bond, not to form a chemical bond. We'll talk about that a little more later in the year. All right, we have three main types of bonding. We're going to talk about just two of them in section 1. The first one is ionic bonding. After completing the first worksheet, you should be able to determine that ionic bonds will always contain a metal and a nonmetal. Metals and nonmetals. Metals are cations, nonmetals are anions. Cations are always listed first. So just looking at a chemical formula, if you see a metal, automatically know that it's an ionic bond. See, we can look at a scale and determine the difference in electronegativity to determine if something is ionic or covalent. But for the most part, we can just generally look at the formulas and say, okay, if it's a metal and a nonmetal, we're going to label that as ionic. Covalent compounds, they share electrons, and it's between two nonmetals. So everything in a covalent compound is going to come from the right side of the stair-step line on the periodic table. We can split covalent compounds up into two different groups. We have nonpolar covalent and polar covalent. Nonpolar covalent is when the electrons are shared equally by all participating atoms. We have an even distribution of electrons, and so all of these negative charges eventually cancel each other out. Polar covalent bonds, this is when the distribution of electrons is uneven. So we might have more electrons on one end of a molecule than another end of a molecule. And this will become more apparent when you learn how to draw Lewis structures, which is later on in the chapter. There will be separate videos specifically for Lewis structures. We can calculate the difference in electronegativity to determine if something is polar or nonpolar. Nonpolar covalent, they have electronegativity difference less than 0.3. Polar covalent, it's greater than 0.3 but less than 1.7. This is a chart out of your book where I got this information from. So 0.3, 1.7, all the way up to 3.3. If you'll notice on the right-hand side, it says percentage of ionic character. So everything at first is considered ionic, and then you have to calculate the percent. So we can't say that something's fully covalent or fully polar, fully nonpolar. We have to give it a percentage of how ionic it is. So really, just about everything we're going to talk about is going to fall somewhere in between. There is a chart on page 161 in your book that gives you these electronegativity values so that you can calculate the difference between two elements. All right, so these are just some generic images. Nonpolar covalent, we don't have any extra electrons. Everything is spread out equally. Polar covalent, you can tell this compound with an element, this one is much larger. It also, these electrons are closer to this element, or to this compound, than they are to this element. So that tells me this compound has more control of these two valence electrons than this one. And then the same thing here, these two valence electrons are closer to this molecule, to this compound, and further from this element. So that tells me that this atom has more control of these two valence electrons than this one. So since these electrons are shared unequally, this one's considered polar. There are several practice problems on the worksheets where you're calculating the difference in electronegativity to determine what type of bond it creates. All right, so that's pretty much it for section 1. We'll go on to section 2. And this one's all about covalent bonds. Anytime we talk about a covalent bond, we refer to it as a molecule. So we don't say that we have a molecule of salt. It's really specific for covalent compounds, so it's a term that's used incorrectly quite often. Chemical formula. This is kind of a shorthand way to write out what elements we have and how many of each element. So we all know the chemical formula for water is H2O. So instead of writing out 2 hydrogen and an oxygen, we have chemical formulas that kind of give us a shorthand way of writing things. The subscript, the number at the bottom, tells us how many atoms we have of that element. Molecular formulas, they tell us type and number of atoms to form just a single molecule. So if we go back, we have this molecular formula, sucrose, which is sugar. That's just one sugar molecule. Just one teeny, teeny, tiny molecule. We have different ways to represent molecular formulas. This is called a ball and stick model. This is a space filling model. This one shows our p orbitals. So we'll talk about the VSEPR theory, valence shell electron pair repulsion theory, in section 5, I believe, in this chapter. And then this is just a regular stick model that we're most familiar with. Monatomic atoms. So this is something that can exist without being bonded. So sodium is the example they give here. Sodium doesn't exist in nature by itself, but it is possible for it to exist. So I have in the chemistry lab a container that has pure sodium in it. There are certain elements that cannot exist alone as a single atom. They have to form pairs, and so we call these diatomic. And this is something that would be good to mark on your periodic table because you'll need to know them later. There are 7 of them. The first one is hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So I would mark those 7 elements on your periodic table and know, put an asterisk or something on the table so you know those 7 elements are called diatomic. So we can't just have F or just Cl. We have to have F2, Cl2, H2, I2. And then polyatomics. This is anything that contains more than 2 atoms. I've already talked about this one, lowering our potential energy to form a covalent bond. So we have different attractions and repulsions going on in a covalent bond. So our nucleus in this atom is attracted to this valence electron, and this nucleus is attracted to this valence electron. But then we also have repulsions. So this nucleus is repelled by this nucleus, and this electron cloud is repelled by this electron cloud. So these forces end up canceling each other out, and this is how we have such a low potential energy value. We talked about atomic radius. A bond length is something similar. The distance between 2 bonded atoms at their minimum potential energy. So this is the closest that they will ever achieve. We've talked about bond energy as well. It's the amount of energy needed to break a chemical bond, not to form one. Most of the time, bond length is measured in picometers. Pico is 10 to the negative 9th. So if our decimal was here after the 5, we would have to move it -9 times to get the distance between 2 nuclei of atoms. These are typical bond energies for our diatomics. When we have covalent compounds, they are sharing electrons, and so when electrons are shared, their orbitals end up overlapping with one another, and this will become more important when we talk about hybridization in section 5. Octet rule, this is one that you probably remember from 9th grade physical science. We know from the last chapter how to calculate the number of valence electrons in an atom. The octet rule tells us that all atoms want 8 valence electrons. Sometimes it's easier for them to give away valence electrons. Sometimes it's easier to gain electrons from other atoms. But no matter what, atoms want to achieve their full octet. They want those 8 valence electrons. We do have some exceptions to the octet rule. Not every single element has to have 8. Hydrogen is our first exception. Hydrogen only has 1 electron. It only has 1 energy level, and we can only have 2 electrons on the first energy level. So hydrogen is happy with only 2 valence electrons. And the same thing with helium. It has 2 electrons. It doesn't want 6 more. It can't hold them. The next one is boron. Boron has 3 valence electrons, and it will usually only bond with 3 other things to give it a total of 6 electrons, and that's okay. So those are the ones that have less than 8. There are certain elements that can hold more than 8. So elements in the main group for period 3, so remember main group elements are S and P. So for period 3, that would be sodium through argon. They have an expanded valence. That means they can hold more than 8 electrons on that outermost ring. Electron dot notation. This is something that Ms. Smith prepared you well for chemistry. Most of y'all will remember this. So what you do is you write the symbol for your element, and you put dots surrounding that symbol to represent the number of valence electrons. There are a couple of rules. You can't have more than 2 dots on any one side. And remember, electrons don't like to pair up until they have to. So if you look at carbon, instead of having 2 pairs of 2, we have 1 electron on each side. So that represents our 4. And then we'll go back and pair them up. Some books give a specific order in which way you should put your dots. Your book generally does right, left, top, bottom. It really doesn't matter. When we get to Lewis structures, you'll notice that Drawing them in that order is not really going to help you any. When we have two dots, two electrons in between two symbols, this represents a covalent bond. So another way we could draw this is we could put a dash in between them. So remember, hydrogen's happy with two electrons. So this hydrogen on the left, it has access to these two because they're sharing. Hydrogen on the right has access to these two, so this bond is happy. Fluorine is not one of the exceptions. It has to have access to 8. But if we look on the periodic table, fluorine has 7 valence electrons. So we can count these 7 for one fluorine, and then we can count these 7 electrons for the other fluorine. They're sharing 2 electrons in the center. So now the fluorine on the left has access to 8. The fluorine on the right has access to 8. And they're sharing the 2 in the middle to represent a bond. So this would be a correct Lewis structure for fluorine. Any atoms that are not part of the bond are called unshared pair of electrons or lone pair of electrons. So all of the ones in yellow, these are unshared pairs or lone pairs. The ones in the middle, the white ones, are part of the covalent bond. I have another video posted that gives more specific information on how to do Lewis structures. So here, on the last slide, we had 2 dots to represent the valence electron that each hydrogen contributed. Well, we can replace those 2 dots with a dash. And so that represents the same thing. So anytime you see a dash, know that that represents a single bond for 2 valence electrons. All right, so single bonds, we're sharing 2 electrons between 2 atoms represented by a single line. These are the longest chemical bonds. Double bonds, so this means we have to share 4 electrons in the center, and we represent it by 2 parallel lines. Double bonds are shorter than single bonds, but they are stronger than single bonds. And then triple bonds, sharing 6 valence electrons between 2 atoms, and we represent it by drawing 3 parallel lines. These are the shortest of all bonds, but yet the strongest. So think of it kind of like the game Pencil Break. If you have a brand new pencil and you're playing Pencil Break, it's probably going to snap in half real quick. But if you have a medium-sized pencil, it's going to be a little bit stronger. And if you have a little short, tiny pencil, it's going to be the strongest. So our bonds work the same way when we talk about strength. The most common elements that form double and triple bonds are carbon, nitrogen, and oxygen. You don't normally see double bonds or triple bonds with any other elements. So carbon, nitrogen, and oxygen are really the only ones that you will see that form double and triple bonds. If you put a double or triple bond on any other element in this level of chemistry, your answer is more than likely going to be incorrect. I don't really use the rules in the book. Watch the next video for Lewis structures. All right, section 3 is all about ionic compounds. So we have that electrical attraction between a cation and an anion. So we have a cation that gave away its valence electrons, and we have an anion that has gained its electrons. So we have a transfer of electrons instead of a mutual sharing. So because of that, ionic bonds are generally stronger than covalent. Ionic compounds are usually going to form very hard solids. They usually have a crystalline structure to them. They have a very organized layout or a network. So here we can see our cation, our metal that gave away its electron, is now smaller. Our anion that has gained the electron has actually gotten larger. And they're very ordered. They're alternating positive and negative throughout the entire compound. A formula unit is when we reduce down an ionic compound to just its lowest whole number ratio. This is the general formula that we see for ionic compounds, are already reduced down. So here we know sodium has 1 valence electron, chlorine has 7 valence electrons. Sodium is going to give its 1 valence electron to chlorine. When it gives its electron away, sodium now has a positive charge and chlorine has a negative charge. So now they're kind of like magnets. We have that positive and negative attraction. That's where we get this electrical attraction from. Crystal lattice is the name we give to ionic compounds to describe their very ordered arrangement. So here is the crystal lattice structure for salt. We talk about an electrical attraction. Sometimes it's also referred as an electrostatic attraction between our cation and our anion, which holds these two ions together to form a bond. So since these attractions are stronger than covalent, they have very, very high melting points. It's going to take a whole lot of heat to melt a crystalline solid. They're very, very hard. When they break in clean lines. They don't just shatter. They're good conductors of heat and electricity when they're dissolved in water, but if they're solids, they do not conduct electricity. Polyatomic ions, this is something that you're going to become very familiar with, and we'll have a quiz over a list of polyatomic ions before Thanksgiving break. So this is a group of elements that are covalently bonded together, and they have an overall charge. If we look at most compounds, they are chemically neutral, but polyatomic ions is a group of ions bonded together that have an overall charge. They either have extra electrons or not enough electrons. So here's an example. Ammonium, NH4, it's 1 nitrogen surrounded by 4 hydrogen, and there's 1 electron short, so it has a positive 1 charge. This NH4 will stay bonded together as one group, and then one other atom will bond itself to the nitrogen. Here's some other ones. Nitrate, which is NO3, sulfate, which is SO4. If you'll notice on the Lewis structure, anytime we draw a Lewis structure of an ion, we put it in brackets and we write the charge on the outside of it, so that way I know you understand that it's a polyatomic ion and it has a charge and you didn't just kind of mess up. All right, section 4, metallic bonding. We don't spend a whole lot of time on metallic bonding. Most of this information you're already familiar with. Metallic compounds are very good conductors of heat and electricity. This is because we have a sea of electrons. The electrons in a metallic compound are free to move around. The electrons are not stuck with the parent atom. And so since our electrons can move, they can carry electricity. This also causes them to be malleable and ductile. So when we go to bend a piece of metal, the electrons can move out of the way to cause the metal to bend and crease and to be able to shape it back. Ductile, so that means they can be drawn into wires. And a shiny appearance, so they have luster. Another way of saying, most books use this term sea of electrons to let you know that the electrons can move around. But really, we call those electrons delocalized. They don't have a specific area that they have to stay in. They can move around freely. All right, section 5, we go over VSEPR theory. So when different atoms bond together, we have overlaps of s, p, d, and f orbitals, and this causes the molecule to form different shapes. And so we refer to this as its molecular geometry. When these elements and compounds form these different shapes, we can look at the distribution of our electrons and look at its polarity. So we can determine if it's polar or nonpolar. All right, so VSEPR stands for valence shell electron pair repulsion. So what this tells us, the valence shell electrons that are not part of the bond repel one another. They want to spread out as far apart as possible. And so when they do, it causes the molecule to change shapes. There is a chart in your book that goes over all of the shapes, and it gives you kind of a generic formula. So here we have 3 elements. We have one central atom. We have 2 things attached. This cannot bend because it has double bonds. So this shape is called linear. Here, for trigonal planar, we have one central atom and it has 3 things attached to it. They are going to be spread out equally. And so we get trigonal planar. Tetrahedral, you have one central atom and 4 attachments. Trigonal bipyramidal. So now we have one central atom and there are 5 things attached to it. So if we cover up the bottom half, we can tell here that this makes a pyramid, and it's a 3-sided pyramid on the top. And then we can flip it over and it's going to look the same. It makes a 3-sided pyramid on the bottom. And so that's where the bipyramidal comes from. Your book has a few more shapes as well, and we'll go through and make a foldable one day later this week. So once you draw the Lewis structure for an atom, you can go through and determine what shape it's going to form. And you can look and determine if it's polar or nonpolar. So in this example for ammonia, hydrogen doesn't have any extra electrons around it, unshared pair of electrons. But nitrogen has 1 pair. So we have extra electrons up here, and we don't have any extra electrons up here. So since we have negative up here, we have a negative end to our molecule, and then each hydrogen is a positive end to our molecule. So now we have poles. We have a negative pole and a positive pole. So this molecule would be considered polar. Similar to water, we have 2 pairs of electrons here. We don't have any extra electrons around here. So this end of our water molecule is negative. This end is slightly positive. So we have a negative pole and a positive pole. So water is also a polar molecule. This is a little more what your book looks like. This column tells us how many things are bonded to the atom in the middle. This column tells us how many electrons are lone pairs. How many of them aren't part of the bond. Here you just get an example, and here they've drawn the Lewis structure for you. Hybridization. So not everything is neat and pretty all in one shape. Not all the electrons are on the same orbital. So occasionally what happens, we might have electrons in an s orbital overlap with electrons in a p orbital, and so they form a hybrid. Kind of like mixing a lab and a poodle, and you get a hybrid type of dog breed, so you get a labradoodle. Well, we're overlapping s orbitals and p orbitals to form a hybrid orbital. So here are some examples of s and p where they've overlapped, and we have a kind of an unequal distribution for our electrons again. Intermolecular forces. So since some of these molecules have negative ends and positive ends, these molecules form temporary attractions between each other. So intramolecular forces would be the forces inside of a molecule holding it together. And we've already talked about attractions between electrons and protons and neutrons. And now it's intermolecular. So we're going to look at the attraction of one water molecule to another water molecule. These are very weak attractions, much weaker than an actual bond. So a dipole is what's created in a polar compound, and we've kind of looked at it already in a water molecule. And here's an example in hydrochloric acid. Chlorine is going to have 6 unshared electrons surrounding it, or 3 pairs of electrons that are around 3 sides of chlorine. Hydrogen doesn't have any electrons around it. So since there's electrons over here, we have a slight negative end to our molecule. We don't have any electrons on this side, so this end has a slight positive charge. So it's created a pole. You have a negative pole and a positive pole. So this is considered dipole. What happens if we take another hydrochloric acid molecule? The hydrogen end, let's see if this is going to show up. Since it has this slight positive charge to it, so this has a negative, this has a positive. The slight positive charge here is going to form an attraction to that chlorine. And then another HCl molecule is going to come along, and it's going to form a temporary attraction here. And so these molecules kind of collide into one another in this order, and then they move on and they form a dipole force with something else, with another molecule. So all of these molecules line up positive to negative. So when they do that, we call these dipole-dipole forces. These dipole forces cause things like surface tension, capillary action. I don't know if you remember that from biology. That's how the leaves get water. The roots suck up moisture from the soil, and the moisture follows up the plant. When you get your finger pricked and the blood goes up the glass tube, that's capillary action. So all of these things are caused by dipole forces. The next type is hydrogen bonding. It's very similar to a dipole force, but it happens specifically with a hydrogen atom. Water molecules produce hydrogen bonding. So the hydrogen, that's the little blue bubble right there, is attracted to the negative end of a water molecule. And then this hydrogen is attracted to the oxygen of this water molecule. And so all these little attractions going on also causes the meniscus inside of a glass container with water. Our weakest type are called London dispersion. What happens is we have an atom that its electrons are rotating around the nucleus. Well, all of a sudden, the electrons both end up on the same side. So if this electron ended up over here, and we had two electrons side by side, well, now instead of our atom being a perfect circle, it's going to have this bulge on the side, and this whole end of the atom is going to have a partial negative charge to it. That's what that funny shape there is, a lowercase delta. It means partial. So if all of our electrons are on this side and it has a negative charge, that means this side of our atom is going to have a partial positive charge. Well, the next atom that gets close to it, its electrons are going to be attracted to this positive end, so all of its electrons are going to line up. And so it kind of has a domino effect. As fast as these electrons are moving, it's instantaneous. As soon as those electrons all move to one side, there's a slight attraction, they move apart. So London dispersion are our weakest of our intermolecular forces. So that brings us to the end of chapter 6.